Another video. So I actually recorded a 20-something minute video of this previously, and it kind of just shut down. I forgot to turn on my mic. So yeah, I'm feeling super tired today, so I'm gonna go super speed run through this, guys. I'm so sorry. So let's look through all the things that we need to do. We need to find Sx. Sx simply describes the cumulative arc length of a function. So let's say that we had a function y equals x squared plus 1 over 8 ln of x. Then let's find the dy over dx first. If we want to find the arc length, that's 2x plus 1 over 8x. And then Sx is simply the integral from, let's say this starts from 1 over x, right? So from x is larger than 1, it's 1 to x. And in this case, it's going to be square root of 1 plus, and then it's 2t plus 1 over 8t squared, this dt. So basically, the reason why we want to keep x and t separate is just because in this case, x determines the length towards which we are doing the integral. So yeah, that's what Sx means. It's simply a definition. Let's move on to the next thing. So next we're going to find the surface area of a volume when we do revolutions with it. So let's imagine that you had a function like this, and you had a curve that looks like this, right? And let's say we rotate it around the x-axis. That means that it's gonna end up kind of looking like a solid that looks like kind of like a bell like this, right? So to find the surface area, we can assume that a little part of here, like a rectangle part, looks like ds right here. So if you revolve the shape around the x-axis, what you end up with is actually a little strip, right? Can you imagine that little strip here? This is the backside. So a little strip that kind of exists. That is a little strip. So it's similar to the integration of like volumes and that kind of stuff. We add up these little strips. So how do we find the strip? Well, we know that, let's unfurl it into a rectangle, and then we can say that this is ds. Okay, now at this point x right here, we know that this is r, right? And because this is a circle, we know that this length along this line right here is just the circumference, which is 2 pi r. And in this case, this function, let's say fx, r is simply the vertical height of the function, which we can say is y, or it can be equal to say is fx. So let's use fx, but we can just say 2 pi y, for example, or 2 pi y or 2 pi fx. Okay, so the area of a strip we can say is equal to just the total area of this, which is simply length times width, which is ds, multiplied by 2 pi y. And then the total surface area would simply be the integral from, let's say if we were finding it from a to b, it would be the integral from a to b of 2 pi y multiplied by ds. And what is ds? Well, ds is simply a small bit of the arc length. And if you remember the equation for arc length, which is the integral of 1 plus dy over dx squared, of dx. So basically, the integral sign is just a summation sign. So a small piece of that, so if this is s equals this, then a small piece of that ds would simply be a small portion of that sum. So it's just without an integral. So what we can say is here is simply the surface area is going to be equal to the integration from a to b of 2 pi y multiplied by the original function for the arc length without the summation symbol. So it's 1 plus dy over dx. Sorry, guys. So tired. Dx, like this. So yeah. I took some medicine, and it's making me super sleepy, and I'm so goddamn tired. Okay, so let's do a few examples really quick. So let's say that we're trying to find the surface area of a sphere. So the equation for a sphere is y equals r squared minus x squared, where a sphere of radius r, and like it exists from minus r to r. Okay. Hey, AJ, just making a video right now. So yeah, so we know that the surface area of a sphere is always going to be 4 pi r squared. And so let's draw this out. Let's try to do this. So this curve is going to look something like this, where this is minus r, this is r, and this is going to be y r squared minus x squared. Okay. So basically, if we were to revolve this around the x-axis, what you'd end up with is something that looks like this. And if we were to try to find the total surface area, we have to start with a strip like this, right? So you can see how it looks kind of like a sphere right now. And if we find the surface area here, it's going to end up like something like this, right? So let's unfurl that lip. Let's try to find the equation for the total surface area, and let's see where it takes us. So if we unfurl that, it's going to look like this. This is going to be ds, and then this is going to be, this length is going to be r So it's going to be 2 pi r, not the other r. Let's just say this is like k or something. 2 pi k, but you know what I mean by 2 pi r. And then k is just the height of the function, so it's going to be 2 pi y. Oh, actually, I forgot to mention something. So now that you know where this kind of r comes from, which informs like this equation right here, there's just a few nuances. Like for example, if we were to do a in terms of y, like revolve around y instead, you can see how the strip that we made, the r is dependent on the x, right? So in that case, instead of using y, so we said y equals fx, that's why we used 2 pi y here. You can also say it's 2 pi fx, right? So in this case, if you had y equals root x and you're doing it around the y-axis, you see how we need the x. We need whatever the x length is, right? So then we'd have to say x equals y squared and use y squared, or we can say it's 2 pi x, or we can say 2 pi y squared. So that's another nuance to know. Anyways, let's get back to this. So it's 2 pi k, 2 pi y, which we can say straight away is also 2 pi of square root of r squared minus x squared. Okay. So then the total surface area is going to be the integration from minus r to r of 2 pi y multiplied by ds, and we know ds, or 2 pi, let's say 2 pi r squared minus x squared, and then multiplied by ds, and we know what ds is. ds is going to be 1 plus dy over dx all squared dx. Okay, so now let's find dy over dx. So let's say y is equal to the square root of r squared minus x squared. Then dy over dx is simply, let's rewrite this in terms of power rule, r squared minus x squared to the power of minus 1/2, multiplied by the power, multiplied by the differentiation within the bracket. So r squared is just a constant. That turns to 0, minus x squared turns into minus 2x. And r squared minus x squared, power of minus 1/2, decrease the power by 1. Okay, so now let's put this into the equation. Surface area equals integration from minus r to r of, let's take the 2 pi out, 2 pi up here, and integration of minus r squared, root r squared minus x squared, multiplied by the root of 1 plus, so let's square off this. 1 over 2 squared is 1 over 4. Minus 2x squared is 4x squared. 1 over 4 cancels, just 4, multiplied by minus 1. So this r squared minus x squared all to the power of minus 1/2. Square of that is just r squared minus x squared to the power of minus 1. And then this is dx. So let's rewrite this. 2 pi of minus r to r, root r squared minus x squared, multiplied by the root of 1 plus, so it's going to be x squared over r squared minus x squared. Do you guys see how that comes? Okay, so now because we have two roots here, we can just multiply this straight into here. So that's going to be 2 pi minus r. I'm going to write out this, but you can see how the denominator cancels here. So it's going to be r squared minus x squared multiplied by 1 here. It's just r squared minus x squared. R squared minus x squared plus, and then I'm going to write it out here, r squared minus x squared multiplied by x squared over r squared minus x squared. So you can see how these cancel out. So this leaves us with the equation 2 pi minus r root of r squared minus x squared plus x squared by itself. These two things cancel out. Dx root of r squared is just r. You can take the r out, so that's just 2 pi r integral of minus r to r of 1 dx. Okay, so this is going to give us 2 pi r, and 1 integrates into x, r to minus r. So then this is just going to be simple to 2 pi r multiplied by r minus r, which is simply plus r. So r plus r is going to be equal to 2r. And you can see how that turns into 4 pi r squared, which is just the surface area of the sphere, which we were talking about. Okay, so I'm going to skip the second example, and we're going to move on to the next example. This one's going to be pretty interesting. So we're going to be doing something called this one. Gosh, it's going to look like this, 1 over x squared, sorry, 1 over x. And if we were to revolve it around the x-axis, this is something, it's going to resemble something called Gabriel's horn. And this, you can search it up. It's basically something with a finite volume and an infinite surface area. And it starts at 1. So 1 to infinity. So let's try doing this. It's going to be pretty interesting. I just think it's a good example. Sorry, guys, if I'm super tired. I did this like already. It's just I forgot to turn on my mic. I'm still tired right now. Okay. So to find the volume, we're going to use the washer method, which looks something like this. So that's dx. So it's going to be simple as just the integration of pi. So the actual equation for the wash method is r2 squared minus r1 squared dx here. But since we don't have an r1 squared, so it's just this. So it's going to be pi. The r2 squared is just the vertical height of the function, which is just 1 over x. So it's 1 over x squared dx. The integral of this is simply, it's basically x to minus 2 dx. Okay, so the integral of this would be pi. Increase the power by 1, divide by the new power. This, and it's just 1 to infinity. I'm too lazy to write the limits in, but if you are doing this, you should write the limits in because this is mathematically incorrect. So that's pi multiplied by minus 1 over infinity minus 1 over 1, which is minus 1, which is just plus 1. Here, this gives us, and the simplification of this turns into 0, 1 over infinity turns into 0, so pi multiplied by 1, which is just pi. So therefore, volume is finite. Okay, but how are we going to find the surface area? So let's try doing the surface area. So to find the surface area, we need dx. So let's find dy over dx really quick, which in this case is just 1. This would be equal to x to the power of minus 1, so multiply by the power. Minus 1 to the power is minus 2, which is just 1 over x squared minus 1 over x squared. And so the surface area here, let's kind of think about what we're doing. So we have a little strip like this. That little part is ds. So we have a rectangle, it's ds, and the height, the r here is going to be 1 over x. That's just the height of the function. It's going to be 2 pi r, which is going to be 2 pi multiplied by 1 over x. And so the area of a slice is going to be ds multiplied by 2 pi 1 over x, and the integral of this, the sum of all the strips is going to be 2 pi 1 over x multiplied by ds, and ds in this case is 1 plus. We know what dy over dx is, so dy over dx squared. So minus squared is positive. We don't have to do anything about that. 1 squared is 1 over x squared, which x squared is x to the 4, and dx. And we're going from 1 to infinity. Okay, and so we need to show that this thing is divergent. So now if you remember from our last class, if you had a function that's bigger than another, right? So let's say this is our original function, and it goes to infinity. But if we have a smaller function and we prove that that one's going to infinity, then for sure the larger function has to go into infinity. So let's find a smaller function than our function. And so if you remember the theorem that it's like 1 over x to the n, where n is equal to 1 or smaller, equal to smaller than 1, then it's divergent. The integral from 1 to infinity of it is divergent. So what we're trying to do is we're going to have to try to compare this original function here to some kind of 1 over x to the n kind of equation. So let's try doing 1 over x. Generally, the idea is sorry, I just bit my lips. Generally, the idea is we want to compare it to 1, and then we end up dividing it by x. So let's start by comparing something to 1. So we can say that 1 plus, let's write out the equation here. So 2 pi integral from 1 to infinity of 1 over x integral of 1 plus 1 over x 4 dx. And we want to compare this to 1. So I think we can all agree that 1 plus 1 over x to the 4, especially since we know that x is larger than or equal to 1, x to the 4, we can say that this is definitely larger than 1, right? Because in the worst case scenario, x equals 1. So 1 plus 1 over 1 to the 4, which is 1. So 1 plus 1 is 2. 2 is larger than 1. That's true. So now let's square both sides to get something equivalent, right? We're getting this section right here. Square both sides. And we can write, so this is still mathematically correct. 1. So square root of 1 is just 1. Okay, now let's multiply. So you can see how we have this part here. Now let's multiply everything by 1 over x. So now we know we have the form that we want right away, because if we were to integrate this, both sides, this would be divergent, and therefore, because it's smaller than this one's divergent. So let's just add on the 2 pi just to prove that it's exactly this equation that we have. If we multiply by 2 pi, this left side's going to get even bigger. So it reinforces this, that it's larger than this other function here. So now that we know, because we know 1 over x, so we have 1 over x to the n when n is smaller than or equal to 1, we know that's the integration from 1 to infinity is divergent. And since that's smaller than this one, we know that that's integration from 1 to infinity is divergent. So therefore now we know that surface area is divergent. Okay, so sorry for being tired, guys. Thank you guys so much for watching.